Hi all of you. Welcome to another lecture of nanoelectronics. This is a topic in the fourth module of KTU syllabus in the subject. The topic is two-dimensional electronic systems. I am Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET Pyramid, leading this session. Let us begin. What do you mean by two-dimensional electronic systems? One of the most important recent developments in semiconductors, both from the point of view of physics and for the purpose of device developments, has been the achievement of structures in electronic behavior is two-dimensional. Okay, the most important development in semiconductors was the achievement of structures, or it was actually from the point of view of physics and for the purpose of device developments, we had one important property which was taken into consideration, that is the two-dimensional behavior of the electronic systems. The major systems where such two-dimensional behavior has been studied was in Morse structures, in quantum wells and superlattices, which we will see while going forward in this lecture. More recently, quantization has been achieved in one dimension, that is quantum wires, and zero dimensions, that is quantum dots, which we have seen already. Now, the first topic for discussion is MOSFET. This is the basic structure of a MOSFET. MOS device is fabricated from a substrate, usually moderately doped p-type or n-type silicon, which together is grounded electrode is called the base. That is, this part will form the base. We'll have this n-type material or a p-type silicon will form the base of the MOSFET. On the top of the base is grown an insulating layer of oxide. That is, the blue color will show the silicon dioxide, followed by a metal layer. That is, the slight yellow color will represent the metal layer. This metal layer is actually the gate and is used to apply the electric field through the oxide to the silicon. For the MOS device shown in the figure, the base region is p-type and we see the base region is p-type or n-type material, and here we have a drain and source which is the drain and source which is p-type as shown in the figure, and they represent the source and the drain, and the base is actually, we draw the base here. Then, this is the basic cross-sectional view of a MOSFET. That is, we have N plus layer is here, then we have oxide is here, then you have a gate, here is the body actually, and here we have source and drain. This is the symbol of a MOSFET. I hope all of you know all these things because we have learned all this in solid state devices. Now, this is the figure depicting the inversion mechanism in a MOSFET. As we know, we have different conditions in a MOSFET. One is the equilibrium condition, second is the accumulation, then we have depletion, and we have inversion. Actually, a large positive voltage applied will give you an inversion property as shown in this figure. Okay, now we have to learn a little bit more about the inversion property of a MOSFET. When a positive potential is applied to the gate, electrons coming from the N plus region and some from the bulk P silicon are accumulated at the silicon-silicon dioxide interface, and these electrons forms the inversion layer. Suppose this is a figure. Some electrons in this N plus region and in the P substrate. Okay, P silicon substrate will form an inversion layer near the silicon-silicon dioxide interface. The inversion layer of the electron is situated in a potential well. The potential well looks like triangular. Okay, we have learned about different types of wells like triangular wells, parabolic wells, and so on. Here the potential looks like triangular. The electron motion is confined in a direction perpendicular to the interface of oxide and semiconductor. The electron motion is confined in a direction perpendicular to the interface of oxide and semiconductor. So the electron motion is actually confined in a direction which is perpendicular to the interface of oxide and semiconductor. The electrons are free to move in the plane of interface, but energy of electron in the well is quantized due to the triangular well. Okay, that is, the electrons will be free to move in the plane of interface, but the energy of electron in the well is quantized due to the triangular well. That is, the energy of electron in the well will be quantized, but the electrons are free to move at their plane of interface. But when the electron is in well, it will be quantized. This is the band diagram of inversion. That is, we have already learned this figure earlier in other subjects, but you have to learn this here also. Just consider the inversion mechanism of a MOSFET while learning this. The possible energy of an electron in triangular well is given by En is equal to 3 by 2 pi into n minus 1 by 4 the whole raised to 2 by 3 E square F square H bar square by 2 m star Z the whole raised to 1 by 3, where we have the value of n ranging from 1 to 3 etc. and F is the electric field strength. So this is the equation for the possible energy of an electron in triangular well. Now what we have to consider more, when it is in free motion. That is, two conditions we have. That is, when the electron is in free motion in xy plane, and also when it is in triangular well. Like I told in the last slide, that is the two possibility of energy storage or how energy exists. One, when it is in triangular well. That is, energy, we said energy is quantized when it is in well, and when it is at the plane, it is free to move. For free motion, the xy plane, the energy is given by E is equal to h square k x square divided by 2 m star x plus h square k square y suffix y by 2 m y. Now m star is given because it is the effective mass. Understood? So the total energy will be the sum of these two. Understood? So we saw we have two conditions for the energy existence. That is, one is due to the energy in the triangular well, the other one is free motion. So the energy will be, the total energy will be the sum of both these two. Then now another simple topic, we have to go into deep in this topic, but now just starting this topic. In the next lecture we'll see about this in detail. But now here we are just going, I am going to brief up what are heterojunctions. Heterojunctions are actually a junction. It is a junction formed by two semiconductors of different band gaps and lattice constant. That is, if two semiconductors have two different band gaps and lattice constants, then it forms a heterostructure junction. A widely used heterostructure junction is the junction formed by gas and gas. We have seen this example many times. Junctions of these types are fabricated with great purity and precision by using molecular beam epitaxy and similar other techniques. So we need very high purity and precision for the junctions of these types. What are the features of heterojunctions? A large concentration of free electrons can be produced in N-type gas by doping. So free electrons, more number of free electrons can be produced. Electrons in gas can move without scattering caused by the impurities. That is another feature of heterojunctions. Effective mass of the electrons in gallium arsenide or gas is very small, hence the mobility is very high. That is, the mobility is found to be high in this case. Now, examples. What are the examples of heterojunction? Resonant tunneling diodes and transistors. High mobility transistor is an example of heterojunction. Optoelectronic devices like lasers and modulators are examples of heterojunctions. Now, when a heterojunction is formed, electrons transfer from gas into gas because the electron affinity in the gas is smaller than in gas. What do you mean by electron affinity actually? What do you mean by electron affinity? It is actually the energy required to excite an electron from the bottom of the conduction band into vacuum level. We have learned all these things before. That is, when a heterojunction is formed, electrons transfer from gas into gas because the electron affinity in gas is smaller than in gas. Now, it creates a depletion in gas and an accumulation region in gas. These are the specialities of heterojunctions. Thank you so much for the patient listening. Hope all of you will understand and learn it well. Thank you.